So this is problem 330 out of the textbook. This is again another coplanar force problem. So with this one we have to determine the maximum mass of the lamp so that the cord system can the maximum mass of the lamp that the cord system can support so that no single cord develops a tension exceeding 400 newtons. So first we're going to start with a free body diagram. I'm not sure where I should start. I'm either at D or C. I'm going to start at D. Yeah, D, because just to tell you my reasoning. Because at point D we have one vertical force and one horizontal force. So I'll draw these, or I'll do a free body diagram. But we have this, and then one that's on both axes. So I think that'll be a little more simple versus the point C, there are two that are on diagonals. So that's just a little bit of my reasoning. But this is point D. So we have the tension from D to E. We have the tension from D to C. And then we have the weight of the lamp. And then we know a little bit about the geometry. We have 30 degrees for that angle. And this is horizontal, and then that's straight down. So let's go ahead and see what we can do. So we know this is our basic equation. Sum of the forces equals mass times acceleration. Acceleration is 0. So we can sum the forces in the x direction equal to 0 and sum the forces in the y direction equal to 0. So we'll start with the x. We have negative t dc plus, free body diagram. You always have to remember to put the x and y axis. So x, y. You usually figure it out whenever you're at that point. But so negative TDC plus TDE. And I want just that x component, so that'll be cosine of that 30 degrees. And then the weight is just straight down, so that isn't part of it. So we basically have two unknowns in this equation. We have TDC equals TDE cosine 30 degrees. We can sum the forces in the y direction equals to 0. And for this one, the TDC is all in the x. We don't have to worry about that. The y is negative W plus TDE sine of 30 degrees. And that's that y component. And that equals 0. So now we have one of the unknowns is the same, but the other one is different. It's that weight. All right, so now we basically have three unknowns, TDC, TDE, and the weight. And we're actually after the mass. So let's change this into, so weight is W equals mg. So we have, let's see, TDE equals, I'm just going to move the weight to the other side, which is mass, and then gravity is, let's see, it's Newton, so 9.81 meters per second squared, and then divided by the sine of 30 degrees. So now we have TDE in terms of mass, and then we can also substitute this into the other equation so that we have TDC, right? TDC equals TDE times cosine of 30. So that would be m times 9.81 meters per second squared times cosine of 30 over sine of 30. So I'm just going to do over tangent of 30 degrees. So now we basically have this, we have two equations in terms of the mass, which is what we're interested in. So we figured out what was going on there. Now we can move to point C and see what's going on in that point. Because with that one, we actually have, one of the tensions will be the same, so TDC, just in the opposite direction. And then we have two other tensions. So we have this, that, and that. And hopefully we'll be able to make some sense of this. So I'm going to go to another page. Alright, so now we're going over to point C, and we're going to draw another free body diagram. So we're pulling that point C, and then we're taking the forces, so T, C, D, which is, the magnitude is equal to the T, DC that we did before. We have TCA and TCB. We know something about this direction. We know that this direction is 45 degrees, and this one's horizontal. So let's go to our equations. So we sum the forces in the x direction equals 0. So we have negative TCA times 3 over 5 minus TCB cosine 45 degrees. We're on the x-axis. And then plus TCD equals 0. So we do know something about TCD, just at least in terms of the mass from the previous page. So let's do sum of the forces in the y direction equals 0. We get TCA times 4 over 5, and that's positive, minus TCB, sine of 45 degrees, that equals 0. So we've got two equations again, or two unknowns in that equation also. So let's see, what can we do now? So we know something about that TCD, or the magnitude of that. So maybe I'll go ahead and put that in terms of the mass. And then we have 4 equations, basically, and 4 unknowns. We still don't know the mass. The mass is what we're looking for. Let's see. Alright, so let's do this one. So we have negative 3/5 TCA minus cosine 45 degrees TCB plus TCD, which is going to be that m times 9.81 meters per second squared divided by the tangent of 30 degrees. That equals 0. And then let's take this equation down. So TCA is going to equal TCB sine of 45 degrees times 5 over 4. So I can plug this value up into that one. Sorry about all the arrows. And we basically get negative 3/5 TCA, which is that 5 over 4, TCB sine 45 degrees minus cosine 45 degrees TCB equals negative m times 9.81 meters per second squared divided by tangent of 30 degrees. They're all negative, so I'm just going to go through, make them all positive. So now we can do TCB in terms of just the mass. So TCB times, let's see, 3 over 4 sine of 45 degrees plus cosine 45 degrees equals m times 9.81 meters per second squared divided by tangent of 30 degrees. I think we're at a point now where I'm just going to change them to numbers because it's getting kind of big. But basically we get TCB, we're just going to divide this from the other side. That equals m 9.81 30 tan divided by, and then we also need to divide by that 45 sine times 3/4, 45 cosine plus, then divide, and so we get m times 13.73. 3 point 7 3. 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 3 and that's still meters per second squared for the units. So we get TCB in terms of M. Now we can go back and figure out what TCA is. I'm just going to put a circle around this one. So TCA equals 5/4 times TCB, so M 13.73 meters per second squared times sine of 45 degrees, and that equals and then 5 times 4 divided by, we get 12.137 times M, and that's meters per second squared. So that's TCA. So now we have basically everything in terms of all the tensions in terms of the mass. And we want to find out the maximum mass. So I'm going to rewrite these on the next page. I'm going to pause it for a second. All right, so I'm just calculating this one out. So it's 19.62 times M, and that's meters per second squared. And then I'm going to do the same for the next one. It was the TDC is TDC equals 9.81 times M over, I think it's the tangent of 30. Yeah, over the tangent of 30 degrees. I just wanted you to know where I got those numbers from. So now I'm just going to divide that out. It's 16.99 times M, and that's meters per second squared. So now we basically have all of these values. We know that the largest one, what did it say? No support, so that the cord system can support, so that no single cord develops a tension exceeding 400 newtons. So I'm just going to look through these. So this one's 13.73 times M, 12.13 times M, 19.6 times N, and 16.99. So the TDE is the maximum tension in the rope. So I'm going to set that tension, so TDE equal to 400 newtons, which that equals 19.62 times M in meters per second squared. And so then we can do M equals 400 divided by the 19.62. And then we get that mass is equal to 20.4, and that would be in kilograms, because newtons is kilograms meters per second squared and meters per second squared. So that would be the answer. And yeah, it just wants to know the maximum mass. So we can always go back to our find just to see what we had put there. Yeah, maximum mass, so that the maximum tension in the ropes is 400 newtons. So that's it.